The last topic we want to cover this week, and we're just going to start it and conclude it next week, is ODE systems. So what do I mean by that? I mean that we're going to look at linear systems in which the unknowns that we have are multiple functions, y1 and y2, for example, and their derivatives depend on each other. So here we have y prime depending on y1 and y2, and y2 prime depending on y1 and y2. This will require us to find slightly different formulations of things. So the first thing we're going to look at is how to write this in an easier format. I think you're all familiar with vector notation, and I'm just going to hide y1 and y2 into a vector, into a variable y. Then my two-dimensional problem gets formally rewritten as y prime equals to ay, where A is a 2x2 matrix. So let's try to just solve it in the same way as we have solved the one-dimensional case. We're just going to claim that y of x is an exponential of the matrix A times x times a vector C of unknowns, C1 and C2. And if we claim that this makes sense, the next thing we have to do is actually define exponential of matrices. Of square matrices, by the way. So let's look at this new topic, matrix exponentials. In one dimension, we can actually define the exponential as an infinite sum of the thing we're using as a power n divided by n factorial. So this means that we're summing 1 plus a squared divided its power, so 2 factorial, plus a at the third divided 3 factorial, and so forth. An infinite sum. And we're just gonna straightforwardly claim that matrix exponentials are defined in the same way. So we take a matrix M, square matrix, real, and we're just gonna claim that the exponential of the matrix M, it's formally the same sum, with m to the power n just being defined as the nth multiplication of m by itself. Because M is a square matrix, so is all its multiplications by itself. So we'll formally also define m at the power 0 to be I, the identity matrix, the matrix with only ones in the diagonal and nothing else. And we're going to formally define the exponential of the matrix M as this infinite sum of m at the power n divided by n factorial. What are the key properties that exponentials have, and how do they relate? Well, in one dimension, we know that the exponential of 0 is 1. And the same way, by how we defined it, we find that the exponential of the matrix 0 being the matrix with only zeros in every single element, is equal to the identity matrix. If we derive the exponential of ax, we find a at the exponential of ax, and this is true in one dimension and in n dimensions. So if A is a matrix, the same holds. In 1D, we have distributivity, so E at the power A plus B is equal to the product of E at the A times E at the B. This is true in higher dimensions only if A and B are their multiplication is symmetric. So A times B is equal to B times A. And the last property that I want to go through right now is that if we do E at the power A, all of it at power minus 1, so we invert E at the power A, in 1D we have E at the power minus A, and the same is true in higher dimensions. Next week we'll be looking more in depth into matrix exponentials and how to compute them. For this week I just want to let you start thinking about it and maybe start reading about it. The second reading assignment for this week is about matrix exponentials, but you have until the end of next week to go through it.